Welcome back, everyone. Get ready to dive deep because today we're taking on the world of energy, specifically how it powers those incredible feats of physics we see every day, like, tossing a football or launching a rocket. And you guys gave us some awesome resources to jump into, especially about simulations. Those are so cool.
Yeah, simulations are a great way to see these abstract physics concepts come to life.
For sure. So, speaking of cool simulations, you sent over this projectile motion energy model, and honestly, it blew my mind.
Oh yeah, what caught your eye about it?
Well, it uses the simple bouncing ball example, which everyone's seen, right? But it shows you how energy transforms during each bounce. It really helps you visualize those changes.
I think that's a key point because we tend to just think, oh, the ball is losing energy, but it's way more interesting than that.
So walk me through this. You have the ball bouncing lower and lower until it finally stops. Where's the energy going?
Okay, so the energy is not actually disappearing, it's morphing, changing into different forms,
Mm.
primarily into heat and sound.
So every time that ball hits the ground, some of its kinetic energy, that energy of motion, gets converted into these other forms.
You got it. It's a bit hidden, but the energy's still there. We hear that thud, and if we could measure it precisely, we'd see the ball getting a little warmer too.
So that warmth and sound, those are the proof that the energy's still hanging around, just in a different disguise. That's pretty neat. And I bet this all ties back to that fundamental law of conservation of energy, right?
Exactly. Energy can't be created or destroyed. It can only transform. That idea is at play everywhere, from the bouncing ball to that rocket you mentioned earlier.
Right, right. It's mind-blowing when you think about it. Okay, so we have this bouncing ball showing us energy in action. But the source material also suggests using this simulation to compare free fall with tossing a ball upwards. What's the point of that? What are we trying to see?
Well, that comparison helps us grasp the dance between potential energy and kinetic energy. Think about it. If you just drop a ball, it's speeding up as it falls, right? More and more kinetic energy.
Right, it's gaining speed, so more kinetic energy.
But if you toss it upwards, it's slowing down as it rises, trading kinetic for potential.
So potential energy is that stored energy because of the ball's height. The higher it is, the more potential energy it's packing.
Precisely. And right at the peak, when the ball stops for that split second, all kinetic energy is gone, all potential energy.
Wow, a complete energy flip. Then, as it starts falling back down, that potential energy gets converted back into kinetic. This is giving me flashbacks to physics class in a good way.
It reminds me of something else the source material mentions, the potential energy reference line. They say changing that line affects the potential energy graph, but not the kinetic energy one. Why is that?
Let's imagine choosing the ground as our starting point for measuring potential energy. If we hold a ball a meter above the ground, it has a certain amount of potential energy.
Okay, makes sense.
But let's say we decide to measure from a table, half a meter high. Now, the ball's potential energy relative to the table is different, even though it's still the same height above the ground. So it's like shifting our perspective where we're measuring from. But the ball's actual energy content hasn't changed, right?
That's the key. The important thing is the change in potential energy as the ball moves. That stays consistent. But kinetic energy, that only depends on the ball's speed, not where we're measuring from.
So it's like using centimeters or inches to measure length. It's still the same length, just expressed differently.
You got it. Picking different reference points can make our calculations neater, but the physics underneath remains the same.
That makes sense, but it's definitely a bit mind-bending when you think about it too much. It shows how our point of view can affect how we understand things. But okay, moving on from reference points, I'm curious about another concept that pops up in the material, work. We use that word all the time, but in physics, it has this very specific meaning.
You're right. So how would you define work in everyday terms?
Well, I think of it as effort, like when I'm lifting weights or writing a report. It's about putting in effort, right?
It definitely feels that way. But in physics, work is all about the transfer of energy. You're doing work on an object when you apply a force to it, and it moves a certain distance because of that force. Like pushing a heavy box across the room. You're applying force over a distance, transferring energy to the box, making it move.
So the movement is key. Just exerting effort doesn't count as work unless something actually moves.
That's the trick. Imagine holding that box up in the air, not moving it anywhere. It feels like work, right? Muscles are burning. But technically, no work is being done on the box.
Whoa, really? Because I'm definitely using energy to hold it up.
You are. But in physics, work is about the energy used to move an object. If it's not moving, No work on the object itself.
Okay, I get it. It's not just about how much effort I feel, it's about whether that effort results in movement. But then what about power? How does that fit into this whole picture?
Well, power is all about the speed, the rate at which work gets done. It measures how quickly energy is being transferred.
Okay, so pushing that same box across the room quickly needs more power than doing it slowly, even if the total work done is the same.
Exactly. It's about the intensity, the oomph behind the work. Think of a powerful sports car. It zooms from 0 to 60 in seconds because its engine has high power output. It can transfer energy quickly.
I'm starting to see the difference. Power is like the energy transfer in overdrive. Now, this brings me to something else the source briefly mentions. Different types of potential energy. We've talked a lot about gravitational potential energy, but they also list elastic and chemical. Can you quickly explain those?
Sure. While we're focused on gravity today, knowing these others helps paint the bigger picture of energy. Imagine stretching a rubber band. You're storing elastic potential energy in it, ready to be unleashed when you let go.
And that snap is that stored energy being released as kinetic energy.
Exactly. Now think about a rocket's fuel. It's packed with chemical potential energy, waiting to be unleashed during combustion.
Oh, right, like a tiny, controlled explosion. And that brings us right back to that rocket question you mentioned at the beginning.
Understanding how these different types of energy work together, that's the key to figuring out how a rocket blasts off into space.
This is also fascinating. It seems like we've only just scratched the surface of this energy stuff. All right, let's keep this energy train rolling. Last time, we unpacked some fundamental concepts like energy conservation, those transformations between kinetic and potential energy, and even touched on how a rocket engine works.
Yes, and it all comes down to that incredible amount of chemical potential energy packed into the fuel.
Right, right. It's mind-blowing. And it made me think about something the source material mentioned, how energy can be transferred between objects. So, how does that play out in a rocket launch? I mean, it's not like the fuel directly pushes the rocket upwards, right?
It's more like a chain reaction, a series of energy handoffs. First, the fuel burns, converting that chemical potential energy into those superheated expanding gases.
Okay, so that's the first transfer. Chemical energy to those super hot gases.
Then those gases are forced out of the rocket nozzle at crazy speeds, transferring their kinetic energy to the rocket itself, pushing it upwards.
Ah, so it's like a relay race. The fuel passes the energy baton to the gases, and the gases pass it to the rocket, propelling it further and further.
I like that. A cosmic relay race.
Mm-hmm.
And think about this. Even the sound of a rocket launch is the result of energy transfer.
Oh, really? How's that?
Well, some of that heat from the combustion process gets transferred to the surrounding air, creating those powerful sound waves we hear as the rocket roars into the sky.
So even that incredible roar is proof of energy in motion, constantly being transferred and transformed. It's like it can't stay still. Okay, so we've got this chain reaction of energy transfers propelling our rocket into space. But the source material also brought up energy efficiency. How understanding energy can help us build better machines. How does that apply to something like a rocket launch?
In an ideal world, we'd convert all the chemical energy in the fuel directly into motion, pushing the rocket forward with 100% efficiency. But in reality, it's not that clean.
Right, there's always some loss, right?
Yeah, some of that energy inevitably gets lost as heat, sound, and other forms that don't contribute to the rocket going up.
So a super efficient rocket engine would be one that minimizes those losses, ensuring as much of that chemical energy gets used for liftoff as possible.
Exactly. That's the holy grail of rocket science. Even small improvements in efficiency can make a huge difference in performance, how much a rocket can carry, and how far it can go.
It's all about getting the most bang for your energy buck. Now, this makes me wonder, is there a limit to how efficient we can make a rocket engine? Are there laws of physics, preventing us from reaching 100% efficiency?
It's a great question, and it touches upon one of the most fundamental laws of the universe, the second law of thermodynamics. It basically says that any time energy is transformed, some of it will inevitably be lost as unusable heat, a concept called entropy.
So even with the most advanced designs, some energy leakage is unavoidable.
Unfortunately, yeah, that's a universal truth, but that doesn't mean we should just give up. Every improvement in efficiency means we're using our resources more wisely and being a little kinder to our planet.
It's about being smarter with the energy we have, for sure. Now, speaking of smart, the source material also talks about common misconceptions about energy, like how some people think it's a substance, a thing you can hold in your hand.
That's one of the biggest stumbling blocks. Energy is not a substance or a force. It's more like a property of a system, a measure of its ability to do work or cause change.
Okay, so it's more like a characteristic, a potential for action, not something tangible, you can't bottle it up. And I guess another big misconception is that energy can be used up or lost, right?
Yeah. Yep, that's a really common one. And it goes straight against that fundamental law of conservation of energy we talked about. Energy never disappears, it just transforms. When we say we're using energy, what we really mean is we're converting it from one form to another, often from a more useful form to a less useful one.
So it's not about energy disappearing, but becoming less available to do work. I guess kind of like how money can lose its value due to inflation.
That's actually a great analogy. It highlights why energy conservation is so crucial. We have to be mindful of how we're using our energy resources, minimizing waste and getting the most out of them. Now, speaking of ways to think about energy, you mentioned reference points for potential energy earlier, and how choosing different points can affect how we calculate potential energy. Does that actually change the physics involved, or is it more like a matter of perspective?
That's a good point. Does it really change anything about the system itself?
The choice of reference point doesn't change the underlying physics at all. It's more about simplifying things, making calculations and interpretations easier. Imagine a roller coaster, for example.
Okay, I love roller coasters.
We could use the ground as our reference point for potential energy, but it might be simpler to use the bottom of the first hill.
So at the bottom of that first hill, the roller coaster has zero potential energy, even though it's still way above the ground.
Exactly. And as it climbs the next hill, its potential energy increases relative to that new reference point. The important thing is the change in potential energy as the roller coaster moves up and down, that remains the same no matter which reference point we pick.
So it's kind of like choosing between centimeters and inches to measure length. The actual length doesn't change. We're just expressing it differently.
That's a great analogy. And this idea of a constant total energy, even as energy transforms, how would that apply to something as dynamic as a roller coaster?
Yeah, that's what I was thinking.
Well, imagine that roller coaster at the very top of that first hill. It's loaded with potential energy, right? Then, as it zooms down, the potential energy is transformed into kinetic energy, giving it speed.
Okay, so at the bottom of the hill, max speed, max kinetic energy.
Right. But as it climbs the next hill, it slows down, converting some of that kinetic energy back into potential energy. And this is the key takeaway. Throughout this whole wild ride, the total energy of the system, the sum of kinetic and potential energy, stays constant.
So it's like a constant dance back and forth between potential and kinetic energy. The roller coaster is a master of energy transformation.
It is. Of course, in the real world, some energy is lost due to friction, like with the wheels on the track and air resistance. But if we ignore those for a second, the total energy stays the same.
It's like a perfect energy budget. No matter how wild things get, the total amount always balances out. This all reminds me of another point the source material emphasized. Energy is everywhere, not just in physics class. It's in biology, chemistry, economics, you name it.
You got it. Understanding how energy works is crucial for understanding the world around us. Think about the food we eat.
Oh, yeah. Like food is fuel, right?
Exactly. Food is packed with chemical potential energy.
Mm.
Our bodies break it down, converting it into kinetic energy for moving our muscles and heat to keep us warm.
So even our bodies are like these incredible energy processing machines, constantly transforming energy from one form to another.
We are. And you know what? This concept of energy transformation applies to so many systems. From the global economy to the evolution of the universe itself, it's all about energy.
It's mind-blowing to think that this one concept, energy, ties together so much of what we see and experience.
It does, and that's what makes it so fascinating to study. It's not just about memorizing equations, it's about understanding this fundamental force that shapes our universe.
All right, I am ready for part 3 of our deep dive. What other fascinating insights do we have in store? Okay, so we've covered a ton of ground, from bouncing balls to rocket launches, roller coasters, and even our own bodies. It's amazing to see how this concept of energy, which can seem so abstract, is actually working behind the scenes of everything around us.
I agree. It's pretty mind-blowing when you think about it. And one of the biggest takeaways for me is how the sun, this giant ball of burning gas millions of miles away, is the ultimate energy source for almost everything on Earth.
It's wild, right? We talked about how fossil fuels like coal and oil are essentially ancient sunlight, stored energy from millions of years ago.
Exactly. The sun is this incredible engine of nuclear fusion, constantly converting matter into pure energy and showering Earth with sunlight. And that sunlight drives pretty much everything, from photosynthesis in plants to the weather patterns we experience.
So even when we're filling up our gas tanks or flipping on a light switch, we're tapping into energy that ultimately originated from the sun.
Pretty much. Yeah. It's a sobering thought when you consider how reliant we are on fossil fuels, these finite reserves of ancient solar energy. And of course, burning those fuels releases greenhouse gases, contributing to climate change.
Right, right. That's why finding alternative, renewable energy sources is so crucial, not just for the sake of innovation, but for our long-term survival on this planet.
Absolutely. And we talked earlier about energy efficiency in machines, but it's not just about building better technology. It's about all of us making more conscious choices about how we use energy.
Yeah, that makes sense. It's like we can't just rely on engineers and scientists to solve the energy problem for us. We all have to be part of the solution.
You got it. It's a collective effort.
Mhm.
Whether it's supporting policies that promote renewable energy, investing in energy-efficient technology, or simply making an effort to conserve energy in our daily lives, every little bit helps.
So it's not just about understanding the science of energy. It's about applying that knowledge to make the world a better, more sustainable place.
I think it's a perfect way to sum it up. Energy literacy empowers us to make informed decisions, both as individuals and as a society.
Well said. And on that note, I think it's time to wrap up our energy adventure. We've covered a ton of ground today, from the basic definitions to those mind-blowing real-world applications.
It's been a blast, and I hope everyone listening feels inspired to keep exploring the world of energy. It's a fascinating subject, and the more we learn about it, the better equipped we'll be to tackle the challenges and opportunities of the future.
Absolutely. A huge thank you to our listeners for joining us on this deep dive into the world of energy. We'll catch you next time.